Welcome back to Machine Learning with me. Today is graduation day. We are officially leaving behind the manual tensor math from our earlier lessons and stepping up to the professional PyTorch tools used in the real world. On screen, we initialize a fresh Python environment. This is where we make the switch. As we import the torch and torch.nn libraries, our objective is clear: completely rebuild our previous breast cancer classification model, making the code cleaner and execution faster. Adopting this framework allows developers to expand architectures from a single layer to hundreds. We can focus on the design of the network rather than the underlying calculus. Look at this code block. This is the standard shape every PyTorch model follows. Inside init, we declare building blocks, one linear layer and a Sigmoid activation. Notice this mandatory super.init line. It lets nn.Module set up its internal machinery before adding custom layers. Now, let's pass 10 dummy samples through. By typing model.features, PyTorch automatically routes data through the forward pass. Check the output tensor printed below our code. You can see the grad FN indicator attached to it, confirming AutoGrad is actively tracking the computation. PyTorch handles the heavy lifting right from line 1. It generates perfectly sized, gradient-ready tensors for our weights and biases, eliminating the need for us to build them by hand. We can easily expand this architecture. Here, we introduce a hidden layer. Instead of going straight to an output, our 5 input features compress down into 3 internal hidden values before making the final prediction. Even with internal layers added, pushing data into the model requires the exact same simple command. We can also clean up execution using nn.Sequential. This tool automatically chains layers together, collapsing a 4-line manual forward pass into a single line. As networks grow to hundreds of layers, this technique prevents unreadable code. Running the torchinfo tool generates this clean architecture summary. You can see the layer breakdown, explicitly tallying 22 trainable parameters, representing all generated weights and biases working together. PyTorch turns architectural scaling into a configuration task. Adding complexity happens within the existing class structure, without touching the low-level logic. Now let's apply this to our real project. We load the breast cancer dataset with pandas and immediately drop the ID and empty columns, since they hold no predictive value. Our data frame indicator shows we are left with 569 patients and 33 columns. We separate out 80% of those patients to learn from and hold back the remaining 20% to test the model honestly on unseen data later. Standard scaling puts all features on the exact same numeric scale. We also use label encoding. Models cannot perform math on text labels like M or B, so we convert these into binary ones and zeros for the network to process. Clean, uniform, logically encoded data is the non-negotiable baseline. Without it, even the most advanced PyTorch tools will fail. Here is our final model architecture on the panel. Right beneath it, we assigned our hyperparameters, the atom optimizer and PyTorch's built-in BCELoss function. BCELoss stands for binary cross-entropy. It is numerically stable, meaning it completely replaces our old handwritten loss function and the manual epsilon clamping safety tricks we had to use before. We now execute the standard 5-step training cycle: forward pass, calculate loss, backward propagation, update weights, and reset gradients. Notice how optimizer.0grad and optimizer.step handle the calculus, entirely eliminating the need to write manual gradient calculations. Look at the loss metric beside the loop. It drops lower and significantly smoother than our Scratch-built version did. This is a tangible, visible benefit of utilizing PyTorch's highly tuned internal tools. Now we test the model. We wrap the evaluation block in a torch.nograd context because we do not need to track gradients during testing. The final accuracy percentage prints directly to the screen. Looking at that result, we need to acknowledge something important. This specific run's accuracy is slightly lower than the manual model we built from scratch in our earlier episode. This happens in real data science. Strict thresholds, like a hard cutoff at 0.9, randomized train and test data splits, and unoptimized hyperparameters naturally create varying results, even when you upgrade to better tools. You have successfully rebuilt a complete project using professional frameworks. All the code from today's session, along with the full day-by-day learning journey, is available at github.com/roheat7696/PyTorch from scratch. If it helped you out, a star is always appreciated. This nn.Module foundation is the standard structure for the larger, more specialized architectures we will build in the next session.